Well, now let's welcome our next speaker, Theodore Faklaris. Theodore is a student from Technical University of Crete.
Yes, and he's going to talk about autonomous vehicles. So what are the algorithms involved and the sensors involved in order to make your autonomous vehicle to move autonomously from one place to another, and also at the same time avoid obstacles, create paths, take into account also directions that are not available, and some other concepts. So let's welcome Theodore to the conference. Theodore, how are you doing?
They're fine. How's everyone?
Everyone here,
He's
great. We are fine. And I think that the audience is all yours. So whenever you want.
All right. Let's begin. Hello, everyone. My name is Theodore Faklaris. First of all, I would like to express my gratitude to the construct for giving me this opportunity to talk today among such great people about my project. And I hope that by the end of this presentation that you gain some valuable information. A brief introduction about me. I began studying ROS in the year 2018, and after some time that I learned the fundamentals, I started creating the autonomous system for the vehicle. Also, right now, I'm pretty much in the ending stages before completing my university. All right, let's proceed now to the presentation. What we're going to do here is follow a very simple procedure to achieve a good level of autonomy for a vehicle operating in an outside environment. Now, the presentation structure is as follows. First of all, there will be an introduction about the vehicle and its sensors. Next, we're going to talk about the necessity of being able to localize the vehicle in the environment and how to do this. Also, when this step is done, we're going to create, based on our vehicle's configuration, a map of the area for providing very useful information to the vehicle and also guide it to our desired goal. After this, we're going to use the 2D LiDAR to provide the car with a live feed about its environmental changes and use this data to avoid dynamic obstacles. And when this is done, the only thing that is left to do is pretty much control the vehicle speed and steering. Now, the vehicle in question is this one right here in the picture. And it's a very special vehicle because this was the very first vehicle created by the students in the Technical University of Crete for the purpose of completing the Cell Eco Marathon in Europe. However, after some time passed, a new upgraded version of it was created, and sadly this one was left behind for a long time. However, in order to not render itself useless, we decided to use it for research purposes. And we ended up choosing to make this into an autonomous vehicle. As you can see in the picture, the vehicle is equipped with a 2D LiDAR that is going to give us valuable information about the environment of the vehicle that's going to traverse in, a camera that's going to be very useful in various occasions in the presentation, two ultrasonic sensors in the front for pretty much giving us information about very close objects in the vehicle, a CPU that we're going to use it to control the vehicle remotely, and lastly, a GPS and an IMU for providing us the position and the orientation of the vehicle in the area. Now, whenever you want to create anything autonomously, the very first you need to do is localizing the vehicle. If you can achieve this, then you cannot proceed with the steps later on. As we mentioned before, the vehicle is equipped with a GPS and an IMU. So theoretically, we could use these two sensors to get the position of the vehicle and the orientation. But if we were to use them independently, then the localization accuracy would be very low. For this reason, there is a very easy solution, and we're going to use the extended Kalman filter method. This is a very common method for fusing various sensor data that we have in order to increase the accuracy that we get in the localization. One side note though, before we start using, the GPS data gives us discrete points in space-time. What we need is continuous data flow. In order to get continuous data, we're going to use the camera, and we're going to use it, and we're going to utilize the method called visual odometry. To put it simply, what visual odometry does is comparing a series of images collected by the camera and finding specific things in its image and determining the space of the vehicle and its speed in the environment. As you can see right here in the picture, we have the GPS. From the GPS, we have two values that we could use. We could use the position that we get and also the velocity. But we choose only the position because the velocity is of very, very low quality. Next, we're using only the heading from the IME. We could also use the linear acceleration, but it would have a very slow error steadily, and we don't want this. And lastly, from the visual odometry, again, we can get the position and the velocity, but we're already getting the position from the GPS, so we're choosing the velocity. And in that way, by applying the AKF, we get a better representation of the vehicle in the area. Now, what is the next part? And that is creating the map of the area. Why do we need a map of the area? First of all, the user needs to have a visual representation of the area in order to easily choose the point that the vehicle needs to go. And another thing is that this map is going to give the vehicle very valuable information. And this is going to be where the road is located in the area. Now, how are we going to find out? We're going to use again the camera for finding the curves in the road. How are we going to find them? Thankfully, this is a stereo camera, and a stereo camera gives us access to depth data in every image. What does this mean? Is that for every image collected, captured from the camera, we know the position of each individual pixel in space. And in that way, we can create a height threshold for identifying where these curves in the area are. And we can, and thus we know where the road is. But let's see this in the ROS space to understand it better. Now, before we do this, I would like you to create a similar configuration like mine right here. What you need to do, first of all, is go right here in the web cell, click it, and place it right here in the bottom. Next, I would like you to click right here to create a gazebo window and place it either left or right, whatever you like. And lastly, click right here to get the RV's window and place it on the top left or top right, wherever you see best. Now, when you're done with this, you're going to get back here to the presentation and begin copy and pasting the following commands. The very first command initializes our simulated environment in the gazebo. As you can see, this will appear in the left window right here. Wait for it a bit. It takes time the first time. Okay. Also, this gives you time to get the configuration done. All right, we're almost done. Okay, this gives you a good time to make the configuration. All right. Okay, we're almost done.
Yeah, Theodore, remember that it took a little bit to load, but I think it's correct.
And right here we have finally our simulated environment. You can zoom in. Also, if you want to see it better, you can maximize the window and minimize it again. It goes to this position right here. And right here, we can see the curves in the area that we're going to use to locate where the road is. Now, our next command is going to load in the vehicle in the simulated area. What you need to do now is click on the arrow right here to add a new tab so that you don't have many windows around, and paste it right here. And right here we have it, our vehicle. All right. Now, we're going to use our next command, which is going to get the depth data that we collect from the camera and map this data in a 2D map. All right, it has begun. We're going to use our custom, this command is going to initialize our custom ROBX configuration to visualize the data. Open again a new tab, paste it. Let me dismiss it so you can see. And right here we have, as you can see, the black spots indicate that they are the curbs, and the white area indicates that there is a road. Now, in order to move this vehicle, we're going to launch this command right here, and we're going to use the keyboard. Again, open a new tab right here, paste it, press K to initialize it. You can increase the speed a bit, and then press W once to see the vehicle moving. You can also see right here a bird's eye view of a vehicle so that you don't have to constantly moving around. You can see right here, also always click in this panel right here when you turn the vehicle. Never lose focus of this. And you can see that we're slowly mapping the area of the map. Now I'm gonna speed this up a bit to get to the very first turn. And I will end the process so we can move on. All right, as you can see, it maps the data perfectly. And let's stop it by pressing 0. You can press 0 right here to end this. As you can see, we're starting to create the map. Now, this is a big map and it's going to take some time, so you can end it right here. Let's continue on now. Also, before you end the process, this one right here, where we have started creating the map, you need to run a separate cell, this command right here, to save it. And we'll eventually get a map like this one right here. Now I know you can see some figures, some green circles, some arrows. We're gonna get to them in a bit. A huge difference that an outdoor vehicle has with an indoor is that an outdoor vehicle needs to respect specific regulations. For example, a vehicle should never go in the opposing lane or enter a forbidden road. Let's take an example right here. Let's imagine that our vehicle is in this road right here, and we want it to go in this position. If we were to imply immediately a grid-based algorithm, it would give us a path like this. But this would be illegal because when you enter this road, it is not allowed to turn into this one. And here come the red circles. This is a node network. To put very simply, we put in key locations in the map imaginary nodes. And these nodes are going to help us guide the car by not having it violate any rule. In that case, let's take the same example again. If our car was right here, then it would go to this node, then to this node, then to this node, and then finally here. Even though this is not the shortest path, right? Keep that in mind. And after we have established the relationship between our nodes, we can move on to the next step, which is how are we going to obtain these nodes? For this reason, a very simple solution to this and a very known one is by utilizing the Dijkstra algorithm for solving these graph problems. But before we are able to use our algorithm, we need to add our car and our end goal into the network. In this image, we have the car. The same thing goes for the end goal too. And what we can do to simply add them is find the closest point, the shortest distance, for example, that the car/goal has from a road. For example, right here, if we go and imagine our car is right here, it finds in this line that it is closest to. And we can return both the nodes. Same thing applies for the end goal. Now, we have a new problem though. Also, there is a separate occasion if the car is outside of the area for some reason, it bounds to the closest node. Now, we have two starting nodes and two ending nodes. Which one are we going to determine to be our starting and which are ending? For this reason, we're going to devise a specific rule that the car needs to point to a node and the goal needs to leave a node. In that way, by applying this rule, we create this flow. And as you can see, is that the car is driving towards the goal. We can see an example right here. Remember, we have these two nodes. If we choose this one as our beginning node and this one as our ending node, then the Dijkstra algorithm will give us back this one, then this one, then this one, and lastly, the car will go to our end goal. If, for example, if we chose the other one, the car would have to turn 180 degrees backwards, go to this, then go back to this, and go to this and to this, and finally reach the goal, which is illogical. And in that way, we solve this issue. Also, there's a very special occasion that the car and the end goal might be on the same road. Before we use the Dijkstra, we need to take this into consideration. What we do is very simply just go straight to the goal. Right here in this section, we have the section of the Dijkstra code that we use. In this section right here, we take a special case that has to do with how the nodes are connected. Here we calculate the distances from each node in order to get the smallest distance. Right here, we have already found our end goal and we keep on searching. We check if the path that we're already going is more is further away, so we don't have to continue. And right here, we change pretty much the parent, the values of the parent node if we have found a better path towards it. Very simple. Now, if we were to use this solution only, it would work only if the car was the only entity in the road, but this is pretty much impossible. For that reason, we need to give the robot a live feed of its environment. In order to achieve this, we're going to use the 2D LiDAR, and we're going to map the 2D LiDAR data into a 2D map. Yet again, it's somewhat the same procedure that we did with the camera, but this time it's going to be easier. And this is thanks to the ROS community for providing us a package that does this exact operation. And the package that I'm referring to is this one right here, the CostMap 2D package. All we have to do is pretty much go into this configuration file and fill it with our parameters. With the most important ones being this one's right here, map size, and the inflation, which I'm going to talk a bit later about this too. All right. Now, as you can see, we have two maps. We have our global map and our local map. Both these maps gives the vehicle very important information about its environment, with the global being where the road is, and the local being where the dynamic objects are. We can see this better right here. Let me close these ones right here and open a new RV session. Our next configuration. You don't have to do this, it's just simply to show you a better view of it. All right. Have a car right here. Let me navigate to this point in the simulation and add an obstacle. What you can do is go right here, in the insert, and navigate down to the P and click on the pickup. Right here, we have a new car. We're going to place it over here. All right. Also, I'm going to run a command in order to see the two maps together. Right here. Let's make this bigger. And as you can see here, our global map doesn't identify the object right here. But if we switch to our local map, we can see it. Now, having this information in two separate maps can be a bit troublesome. So what we're going to do is to merge this information into one map. And this map is going to be the map that we're going to use our next algorithm to dynamically avoid the obstacle. You can see it right here. If we click right here on the merged map, we have both the information combined in one map. Now, how do we get this merged map? You can see very briefly, this is the merged map is the highlight area. All you have to do is pretty much navigate to the bottom left pixel of the map and get the corresponding cell of the global map. And what you do is pretty much filling this map by comparing the values of both the local and the global map. We can see the code segment right here. We get the coordinates of the cell that we're talking about. Right here, we take a special location where the local map might be outside of the global map. It doesn't really concern you. And right here, we get the cell that corresponds to these coordinates. And pretty much right here is that we fill our merged map. All right, now that we have our merged map, we can use our next algorithm. By simply following the nodes, the car is unable to avoid obstacles. So what we need to do is to override this by applying a new algorithm. For this, we could use again the Dijkstra algorithm, but we can use a better one, an upgraded version of it called the A star. This is going to provide us a path faster and in some cases more accurately. However, whenever we are applying algorithms in a grid-based map, there is a certain problem that arises with almost all of them. And you can see it in this picture right here. The green cell is our car, imagine, and the red one is our ending goal. The path that the A-star provides us is the orange one right here. And as you can see, it approaches the edges of the map, meaning that it goes very close to the pavement and has this zigzag behavior, pretty much making it a bit unstable. This can be dangerous. How do we alleviate this problem and get this line right here? It's very simple. All you have to do is calculate the path that the A-star gives you and check an imaginary ray that starts from the beginning cell to each and every single cell right here. For example, if this is our starting point and we want to check this one right here, imaginary ray that begins from the center of this square and ends to the center of this one. And what we do is to check whether this ray hits an obstacle. If it does not, then we keep the ray and we remove this part right here. If it does hit, we keep the pre-calculated path that the A-star has provided us. And we keep on doing this until we reach the ending goal. This is the segment of the code that does it. Here we get the coordinates of our starting cell, our ending cell. We calculate the distance of each other, and we check in this section right here if the ray does indeed hit an obstacle. Now, one more thing that we need to do is that since, as you can see right here, our vehicle is going, the algorithm is going to operate only in this map right here. Let me close this so you can see it better. As you can see, it's small. And what we did before is that we put, let me show you right here, in the map specific nodes to guide our vehicle right here. Our vehicle is right here for this specific occasion. And our next node is this one right here. But as we can see, it's outside our merged map. So our algorithm would lack an end goal, and it wouldn't work. One simple way to fix this problem is to translate this point onto the border of our merged map. And how we're going to do this? Very simple. As we know, the car is always going to be between two nodes, and these nodes create an imaginary line to one another. And what we do is, for example, in this case right here, imagine there is a node right here and a node right here. We check the closest point that intersects to the node that we are going to. For example, in this scenario, we're gonna take this point right here and translate this node, this point right here, as you can see in this image right here. Now, we talked about previously about also you can see right here an image where why are we using this? Why we're overriding our path that the Dijkstra algorithm gives us. For this example right here, if we were to simply follow the green line, we would bump into the vehicle right in front. But as you can see, the red line, which is our A star, it avoids it. Now, as I mentioned before, to take in consideration two things: the map, the size of the map, and the inflation. Why do we need those two things? Now, if our merged map was bigger, it would mean, let's go right here, that there would be more cells for the A star to explore. This would make, even though it would give the algorithm a better understanding of the environment, it would make it severely slower. And also, the resolution plays a part in this. For example, the size of the cells. The smaller they are, again, the more cells you will have to calculate. So what you have to do for the size of the map and the resolution is that you need to find a nice balance between both of them. And lastly, we're going to talk about the inflation. What the inflation does. If we go back here, you can see that the red line indicates where our object is, but we can see that our object is bigger than it actually is. And that's what it does. It creates an imaginary fake obstacle in order for the vehicle to avoid, because every algorithm treats every robot, every vehicle as a point in space. And if we were not going to use this inflation, half of the vehicle would always bump into an obstacle. And that's why we do this. And now we're approaching the last step, which is controlling the vehicle. The vehicle has speed and steering. For the speed, what we're going to do is extremely easy. The only thing we have to do is implement this equation right here, which corresponds to this graph. What this means is that the further our goal is, for example, our current target node is, the faster the car will go. And the closer it gets, it's going to slow down. Very simple. However, for the steering process, it's going to be a bit difficult. As we know, there are many ways to balance a steering model, and we can use very renowned methods are a fuzzy or a PID controller. But by using these methods, it takes a bit of time in order to produce acceptable results. What we can do instead is to implement a new method called regression. What does this method do? It, provided some data, it is going to try to use a mathematical expression to best fit this data, which means that it's going to create for us our control model. Now, what data are we going to collect? The data for our case is the angle error the vehicle has with our goal, and how much steering do we give the vehicle in order to correct it. Now, how are we going to collect this data? If you have any process right here open, you can close it now with Control-C. All right. Now we're going to launch our next simulated environment, which is going to be for the training of the vehicle. Wait for it to close. And now paste the command. Wait a bit. It might getting some online entities in order for it to load.
Theodore, I think that gazebo got stuck. Could it be? If it gets stuck, you can close it and launch it again. Sometimes happens with the gazebo.
All right. Let's check if.
Wait a little bit more.
Okay, let's wait a few seconds.
Okay.
Let me relaunch. It might have crashed a bit. All right, let's relaunch it. All right, and there we have it. This is going to be. Let me maximize this in order to see it better. This is going to be our training environment. As you can see, we have put in a specific location some numbers, and these are going to be the numbers that the car is going to follow, and we are going to be the ones that are going to provide the necessary steering value in order to get to each one of them. So we will start with the first one, then go to the 2, and then to the 3, etc., etc. All right, let's launch our vehicle into the simulation. Here in the new tab, check if everything is closed. And there we have our vehicle. Now, we're going to use our keyboard here. A small disclaimer, for this specific operation, you're going to need to use analog input in order to get a good quality of data. With the keyboard, you're going to get very low. But for the sake of showing you this, we're going to use the keyboard. And now right here, this command is going to capture our data. In order to see this better, let's go right here and then press on the plus sign in order to have it in a separate window. Can make it bigger and paste the command. Okay. As you can see here, it shows us the angle error the vehicle has with the one and how further it is. All right, let's try to fix this. Let's turn the vehicle.
5 minutes to finish.
And starting going to our point. We can do this with every single one of them. Just for the sake of time, I'm going to end this. Can press again 0 right here. Also, when you're done, you can press Control C right here, and your data is going to be stored inside the cutting workspace, SRC, cartouche folder, SRC, and it's going to be right here. We already have the necessary data. And by having the data, we can move on to the next step, which is creating a model to predict it. For that reason, we're going to use the TensorFlow model. And to make it simpler, we're going to use the Keras API. Right here in this segment, we're loading the data. We create our model. And here we add our layers, with the most important one being the activation function. This is going to be the mathematical equation is going to try its best to fit in with our data. Also, I forgot to mention that after you collect the data, you need to group it in order to minimize any noise possible. And after you're done, you can plot the data with your prediction model, and you're going to get something like this right here, with the blue squares meaning the data that you have grouped, and the green line being the steering value that the model predicts. All right, with that done, we can officially go and see the vehicle in action. All right, again, close everything. Close this window, you don't need this. Close everything right here. Launch our final simulation. It's gonna be our next map. Wait for it to close. All right, copy and paste. As you can see here, we also have a dynamic vehicle approaching. The next one loads our current simulation. Put in the next tab. Right here. We're gonna launch our merging map algorithm. Right here. Next, launch our algorithm for the navigation. Right here. And lastly, runs our TensorFlow model and our controlling speed algorithm right here. And lastly, we're going to launch our custom RVS configuration in order to visualize the data. Open a new tab, paste it. Also, you can click on the merge map right here in order to see the combined information. Now, when this algorithm begins, says start, for example, you can place an end goal in the RVS window. Wait for it a bit because it loads the model. The first time it always takes some time. All right, what you have to do right here, let's maximize this, is to press right here on the 2D navigation, see the purple arrow and click it somewhere in the map. As you can see, the vehicle begins, it avoids a car. Also, the car right here is on the wrong lane. Let me delete this before it. Okay. All right, nice. It was intentionally on the wrong lane in order for our vehicle to avoid this. And what you can do right now is to make this a bit more interesting. You can navigate right here and go again on the insert, navigate again back down to the pickup and place some right here, so you can see how it avoids them. Some static obstacles. Here, go back again. Here, maximize this, move a bit, and let's say we want our vehicle to go around here. All right. You can also see this in the gazebo. You can see right here that our restart algorithm avoids the vehicles, whereas if we were to simply follow the green line, the car would crash on these cars. And with that said, you can keep on setting goals in the map and see how the car behaves. But for the time's sake, also, I have implemented this algorithm in a real vehicle, the vehicle that I showed you in the picture. And you can see it in a real environment. Right here, this is the map in the parking lot of the university. And you're going to see that it's for specific occasion that the car is going to deviate a bit from its path. Now, even though the EKF gives us a better accuracy in our localization, we can only do so much. So you can see here some things to make the localization better. And also an appendix that I also included some information on specific things that need a bit more touching. And with that said, the presentation is over. And I would like to thank you very much for being present right now. Thank you very much.
Thank you, Theodore, for your excellent presentation.
Thank you. Thank you.
Thank you. And now let's go for questions to the speaker, to Theodore. If you have any question, then you can put it on the questions tab that is located on the conference panel. And also you can vote for the other question that somebody else has put it there. I will be asking those questions to Theodore now. And okay, now we can see you. Perfect, Theodore. And then let me go with the first question by Yu Wen Chen. And then he says, so he's asking about if you have included, when you are creating the map, if you are including any matching method for the outdoor localization. Because in his experience, the position of the car based on GPS is a little bit unstable. So what can you say about that?
When I was, for a real environment, when I was creating the map right here, as you saw, I needed to pass it many times in order to get a very good representation of the area. Because as he mentioned correctly, a GPS can have a 4 to 5 meter error. However, in our case, I also used the EKF filter, and based on the velocity that the camera provided me, it minimized the error tremendously. But as you can see in the video, the vehicle moves very slowly, and that's the key point. If it were to move faster, then the error would increase. That is the price we take in order to have as good as localization as we can get with this configuration.
Yes. Okay. Yeah. So that's an introduction to autonomous vehicles. So it's
you can also make it better with a 3D LiDAR, and you can have a simultaneous localization by getting a 3D representation of the area, and it boosts its localization tremendously. But in our case, we only have the 2D LiDAR.
And then in that case, we wouldn't use GPS data, but
you can use the GPS data to get a starting point. You don't need to get it continuously. As you can see here, this is GPS dependent. You can see that sometimes it deviates from its path because it loses signal, and that.
Okay, let me go for another question. Let me see. So what is the difference between the gazebo model that you have of your car and the real vehicle that you have? That's a question from Shashank Bhushan.
There's not that much of a difference. I pretty much map the properties of the real car onto our simulated vehicle in order to get as close to the same results I will get. For example, how much steering do you give, the weight of the vehicle, its dimensions, how fast can it go. The only difference is that I can think about is that the data collected in the simulation is way better, more accurate than the one in the real robot.
Yes.
But you use the simulation to get an idea. You don't really use it to test it. When you have created your algorithm, you put them in the real vehicle, you get in the real environment, and what you can do is then make some filters, decrease the noise, as I said, make the car go slower so that it doesn't deviate a lot of the path and increase the error, and things like that.
Okay. Let me go for another question. Okay, so here this has been already answered about the multiple robots. So actually you answered during your presentation, you have put them. Then Gianmarco Pisanelli, he is indicating if you know about the Manhattan, using the Manhattan distance.
Yeah, it uses the Manhattan distance, yeah.
Okay, so it's using, you are using this one.
Yeah,
okay.
Yeah, it's not using the Euclidean, use the Manhattan, yes.
Okay, so then answer the question. Let me go for another one. Then Ion Circle, he says, have you tried to use the sensor fusion system provided by the robot localization, the ROS package that fuses all the sensors?
Yeah, yep. This one I didn't use. I created my own AKF version because when you fuse it, it doesn't take into account the continuous data. It just always maps to the GPS. If you were to use this and fuse the sensors as they are with the localization provided by the ROS community, it would always teleport your car whenever it gets a new GPS position. So what I did, I made my own where it takes into account before changing position, the position that it has already been given by the continuous data so that it doesn't teleport a lot.
Okay.
That's what I did.
Okay. So we don't have any more time for more questions. Then I would like to thank you for the presentation and see you around the universe.
Thank you.